All right, so last week was all about model-based methods. We looked at a couple of different ways to do it, but they were all model-based. We had trend plus seasonal models, we had autoregressive models, things like that. What we're going to talk about today are what are typically called forecasting methods. So there's really no model involved per se. These are techniques where we're trying to follow the time series. The simplest one is something I'm sure you've all heard of, is called a moving average, or to be more precise, we have an M period moving average. Basically what that means is our forecast for the next period. So if we're at time t, we want to forecast what the series is going to be one period from now. We just average the last M data points, right? So we're averaging the previous M data points. So kind of underlying use of a moving average like this is that the time series is more or less stable. And by stable, I mean it's not going up or down in a trend of any kind, right? It may change values from time to time, but basically it's stable. So, one issue in a moving average is, how do we choose M? How many data points do we average together? The last 5, the last 7, the last 10, how do we pick M? So basically the answer to that question is, with a large M, you get a greater averaging effect, which is the same as saying you reduce the variance by having a larger M. However, if the time series sort of changes its level, then a large M, it will take a long time to catch up to that new level. So a smaller M is more responsive to changes in the time series. All right, so I made up this example. So the blue line, the blue here is the true mean, right? So this would be my best guess. So basically this time series, it's just varying around a mean, but the mean changes every so often, according to this blue line. So the series I generated in orange is basically just take the blue line and add white noise on top of it, or normally distributed noise on top of it. So I don't know what the blue is. I can't observe that. All I observe is the orange, right? So now if I do, say, a 5-period moving average, the gray is the 5-period moving average. Right, so you notice it has, its variance is less than the time series itself. That's because I'm averaging, right? So the moving average is closer to the blue than the orange is. If I did a 15-period moving average, that's this lighter orange line. So now you see the variance is even more reduced, right? So generally speaking, it's closer to the blue line. However, when the series changes levels, like it does here around time 30, it jumps up. Notice that the 15-period moving average takes a long time to catch up to the level of the time series, right? And the reason why it takes a long time is because it's averaging in all of these old data points that were at the lower level, right? Conversely, the gray catches up more quickly to the new level, but has higher variance, right? So, those are the pluses and minuses of big versus small period M. I took the actual data out, and now I'm showing the same data here without the actual time series. It's just the 5 and the 15-period moving average. Okay. Now, the next method, it's kind of similar to moving average, is called simple exponential smoothing. So at each time period t, we're going to make a forecast for the next period. So this here says the forecast for time t plus 1 made at time t. And we'll let xt be the actual outcome at time t. And we're going to have something called a smoothing parameter, which is alpha. In a loose sense, alpha is similar to m in a moving average. So the simple exponential smoothing, you can write it a few different ways that are all equivalent. We take the forecast from the previous period and we add to it the forecast error in the previous period multiplied by some alpha. So let's say our forecast last time was a little low, meaning that x minus f is positive because the forecast was low. Then we're going to increase a little bit our forecast for the next time period. So that's one way to think about it. Oops, sorry. Another way to think about it is we're going to multiply our previous forecast by 1 minus alpha. We're going to add to that the most recent outcome times alpha. Okay, so if you look at these formulas are equivalent, by the way, as it turns out. You can look at this one as we're going to adjust the previous forecast based on the forecast error. Here you can look at it as a weighted average of the previous forecast and the previous actual value. If you take this and do some algebra, oops, what the heck? If you take it and do some algebra, you can expand it out. And the forecast you get is you take the most recent observation times alpha plus the second most recent observation times alpha times 1 minus alpha, the third most recent observation alpha times 1 minus alpha squared, etc. So it's a weighted average of past observations, but these weights decay geometrically as we go backwards in time. So the way I look at it is if you look at how past data is weighted in, say, a moving average and exponential smoothing, this would be a 5-period moving average where the last 5 data points we give an equal weight to, and then any data points after that or previous to that get 0 weight. Whereas exponential smoothing weights past data in a fashion that decays geometrically. Right, so for me, when I look at this plot, it basically, intuitively to me, I like exponential smoothing better. It gives more weight to the more recent data points, less weight to the further back in history data points, but it still gets the same kind of averaging effect because it's a weighted average that we get from exponential smoothing, right? Let's just see right here. All right, so simple exponential smoothing or moving averages for that matter, they're appropriate when your time series it behaves kind of like a constant plus noise. In other words, when it's doing basically like this blue line here. It's stable, then maybe every so often it changes its level, but there's no trend going on, right? It's not trending up or trending down. When you have a time series like that, that's when exponential smoothing is appropriate. So when you look at this plot here, how the weights decay geometrically, right? So the bigger is alpha, the faster the weights decay. So if you have a big alpha, you're putting almost all the weight on the more recent data points, and very quickly these weights go down to 0. So it's kind of the equivalent of having a moving average where m is small. Conversely, when alpha is a smaller value, the weights decay much more slowly, and that's kind of like having a moving average with a big value for m, right? So by controlling alpha, you can have it like a longer term memory or a shorter term memory, and you get the same results you did with moving average when it comes to reducing the variance and also tracking up to a new level. So if alpha is a very small number, it'll take a long time for exponential smoothing to catch up to a new level in the time series. So here's just another example. where you have the actual time series data, the dark blue, and then two different exponential smoothing forecasts. The pink has a smaller alpha, the yellow has a bigger alpha, the yellow has more variance, more variability, but it will lag behind a change longer. Okay. So here is I guess, is that the same? I don't know if this is the same example or not. But I generated this example where the true underlying mean is yellow. So it's a stable series that changes its mean every so often. And we can see that the exponential smoothing is kind of tracking that fairly well. Okay, this is just another example I threw in today. This is another important time series. And I thought I would try and plot moving average with period 7 and exponential smoothing with a value of alpha that's approximately equivalent to that. And they both seem to track it okay. Now, one thing you can do is you can keep track of the forecast error. So the forecast error, where am I? Oh, sorry. Okay, the forecast error is just the actual outcome minus the forecast, right? So I can't believe I didn't put that in here. The forecast error would be the value of the time series at time t, that's x of t, minus the forecast for time t made one period ago. So if I can write it in somewhere. Would be x of t minus, oops, sorry about being so slow, the forecast for time t that was made at time t minus 1. Right, that's the forecast error, right? So if I square it, add them all up, take the square root, I get what's called the root mean squared error. So it's a measure of how good my forecast is, right? My forecast, this is my forecast, this is my actual value, the difference is the forecast error. So what you can do is you can implement exponential smoothing and then try different values of alpha, compute the root mean squared for each value of alpha, and find out what gives the smallest forecast error. In fact, you could use Solver to do this. So for the time series I showed you back, this one, I believe, this is that plot. So basically you can look at this and say, okay, the value of alpha of around 0.25 gives me the smallest forecast error. So that's what I'm going to go with. All right, so when exponential smoothing is appropriate, alpha usually tends to be somewhere between 0.05 and 0.3. If you were to do an analysis like this, but the results give you a value of alpha that's significantly larger, that's a good indication that exponential smoothing or moving averages for that matter are probably not appropriate. I'll say one more thing. A lot of times when you plot the actual values versus the forecast, sometimes you get something like this. So this is with for time series with alpha equal to 0.9. So when you look at this, you got to ask yourself, is this a good result or not? You might be fooled into thinking it's good, but what's actually happening is the errors are pretty big. So the red bars here are the errors. So an alpha is a big number. Basically, that's like saying our forecast for next period is just going to be whatever it was last period, right? But when you have a stable time series with lots of error, lots of noise around it, turns out to be a lousy forecast indeed. All right, so just keep your eyes open for something like that going on. So here's a case where I did my root mean squared versus alpha analysis, and I got a high value of alpha. Here you got to be careful and think maybe it's not the right method to use. So this is another time series. The actual data is in dark blue, and I believe this is the yearly levels of Lake Huron, if I'm not mistaken. Then I also show on there exponential smoothing with two different values of alpha. I did the root mean squared analysis on this, and it's telling me I should use a very high value of alpha. So I told you before that when a time series has a trend in it, exponential smoothing is a lousy, so is moving average. This seems to have a trend in it, so that's probably why I got these results. Okay. When you're doing exponential smoothing, there's one minor issue you have to worry about, which is how do you start it out at the beginning? And I think it would be easier for me to just show you in Excel, if you don't mind. Okay, so here's some data. Happens to be daily positive
Professor
coded.
Storer, we cannot see your screen.
Yeah.
And although I sent you an email for last year's forecasting slides, it has the error part if you would like to show it.
Has the what part?
I sent you an email last year's forecasting slides if you want to show it.
I'm not sure why I would want to.
Okay.
All right, so this is just the time series, all right? So if I want to do exponential smoothing, so this is called exponential smoothing, all right? In the first data point, I just make it equal, right? Then the next one, I make it equal to alpha times the previous value times 1 minus alpha, 0.8 in this case, times the most recent observation of the time series, right? And I can just drag that down. Oh, that worked great, didn't it? What the hell happened here?
A2, it should be. It should be plus, Professor Storer. You're multiplying everything.
Oh, okay, thanks. Plus. Okay. Now I can show the two plots, right? And you can see what exponential smoothing looks like. So now the other thing is, now here I am down at the end, right? So I've blown through all of my data, and I want to. So this is the current time, right? So this will be my forecast for for tomorrow. Basically, will be given by this, right? And then I can Let's see, does this work? Well, then basically that'll be my forecast going forward in time, right? Because I'm just trying to follow the mean of the time series. So my forecast into the future will be just whatever it is for tomorrow. All right, so that's kind of how I started off with exponential smoothing. So it turns out that if your time series has a trend in it, exponential smoothing will lag behind it. So for example, suppose my data is a straight trend, just like this. So suppose this is my data, right? If I apply exponential smoothing to this with a alpha equal to 0.5, I get the yellow. If I apply alpha equal to 0.2, I get this pink, right? So the point is exponential smoothing lags behind. You'll always have, you know, in this simple case, you'll have this amount of error every time period. You'll be low every time period. So that's why exponential smoothing is not good for time series that have trends in them. Okay, so there's something called double exponential smoothing that works when you have linear trends in your time series, right? So I changed my notation a little bit here, for which I apologize. But my forecast value, or my smooth value, is the previous value times 1 minus alpha plus alpha times the most recent data point. All right, so from my time series x of t, I can compute these smooth values s of t. That's what I just did in that Excel sheet. Now what I can do is do double smoothing, which basically I take the column of these s of t's, not the x, but the s, and I treat that column with exponential smoothing again. So I smooth the smooth, right? So this is my second order smoothing is equal to alpha times my first order smoothing value plus 1 minus alpha times the previous second order smoothing value. All right. So it turns out that if my data is a trend, single exponential smoothing lags behind the trend, and the double exponential smoothing lags even further behind the trend. However, it turns out that if I take 2 times s of t minus s2, I take 2 times the single smoothing minus the double, it compensates and actually follows the trend exactly. So if I go back to my data, right, this was, I'm now going to, oh, come on, stop it. I'm going to call this my single smoothing, right? And then my double, or my S2, right, call it S bracket 2. I just do it again, right? I said this is equal to this. And I say this is equal to 0.2 times the most recent value plus 0.8 times previous, right? All right, so that would be my double smooth, and then my forecast in double smoothing would be equal to 2 times the single minus the double, and that would be my double exponential smoothing forecast. All right, so if you have something with a trend in it, double exponential smoothing might be what you want to use. So here what I did is the underlying mean of the series is in the dark blue. That's the underlying signal that I don't know what it is. On top of that, I added some noise. So the actual time series that I'm viewing is pink. So I don't know the blue. If I knew the blue, I'd be in great shape because that would be my best forecast. But I don't know it. All I know is the pink. All right. So if I apply single exponential smoothing, I will get this yellow. And as you can see, it lags behind the trend. And so you always have significant forecast error. The forecast is always too low. Once you hit a flat spot, it does pretty well because, well, that's what exponential smoothing is good for. And then it kind of lags above a downward trend when it goes back down. Double exponential smoothing follows the trend quite nicely. However, you'll notice that when it levels off, it overshoots and has to kind of come back to the level part. And then again, it tracks the downward trend pretty well. So if you have something with a trend in it, double exponential smoothing would be the way to go. All right. So the next model we're going to, the next forecasting method we're going to talk about is Winter's seasonal methods. So the way I would describe this is it's exponential smoothing for seasonal data. And there's basically two versions of Winter's model. One is called the multiplicative and one is called the additive. And basically these are forecasting methods when your time series has trends and seasonal components, right? And Winter's, just like exponential smoothing, it's kind of a smoother that places greater weight on more recent data. So the multiplicative model kind of behaves like this. There's a trend in it, so we have an intercept and a slope, right? So it is a trend as a function of t. Then we multiply it by the seasonal adjustment factor. So tau is the season, right? So if it's monthly data, tau would go from 1 to 12, representing the 12 months. All right, do I have the additive version? The additive version, I would add the seasonal adjustment correction instead of multiplying by it. That would be Winter's additive model. And we did a model last week where we had an additive seasonal adjustment term, if you may recall. All right, in this case, we're going to make the assumption that the sum of these seasonal adjustment factors is equal to L, where L is the length of the season. And we'll note that the amplitude depends on the level of the series. So I'll have to show you what I mean. So this would be an example of a model you'd get if you had a 3-period or 3 seasons in your time series, an intercept, a slope, and then depending on which month it is, you multiply by one of these adjustment factors, right? So for example, if we had a time series that looked like this, first you'll notice there's an overall trend. It's my intercept plus my slope. And then there's a seasonal term. And so for the season that has the high value here, the peak, it differs from the trend line by a factor of 1.5 or 150%. Similarly, the season that where it's at its low point, it differs from the trend line by a factor of 50%. And if it's the middle season, it's right on the trend line. That's where I get my multiplicative factors. This adjusts it up by a factor of 1.5. This adjusts it down by a factor of 0.5, and this leaves it right on the trend. All right, so you see how these add up to 3 because it's a 3-period season. Now, when you look at the time series, you'll see it has a trend. You'll see that it has seasonality, but you'll also see that the amplitude of the variation increases as the level increases, right? So you often see this in time series data. For example, this was the Australian wine sales data that we presented last week. You can see there's definitely a trend. Over the long term, it's going up. You can see there's definite seasonality. These peaks are 12 months apart. But you can also see that the variation from the top to the bottom is bigger here than it is over here. That's because the variation is increasing with the level. It's often the case that that happens in time series. So it's in a case like this where the multiplicative Winters model would be appropriate. Now, implementing Winters model is kind of complicated. Once you see how it works, it's not too bad, but it takes a while to figure it out. I will warn you that this is one of the homework problems. So it might not be a horrible idea to actually pay some attention here. So we're going to smooth three different things. We're going to call them the permanent component. That's A, and you can think of that as the current level of the time series. And we're going to smooth the trend component. That's basically the slope. Then we're going to have the seasonal components. Those are the seasonal adjustment factors. And we're going to keep track of each one of these. We're going to update them every time we get a new data point. And we're going to update them the same way we did before by smoothing. Right? We have alpha times the most recent data point plus 1 minus alpha times the previous estimate. Or we can have different alpha, beta, and gamma for each of the components, or they could all be the same. It doesn't matter. Okay. So basically it works this way. After observing the most recent data point, we are going to update our forecasts. All right. So the first thing we're going to do is we're going to update the level component of the time series. So we take the most recent data point and we divide by the seasonal adjustment factor. So what we're trying to do is we're de-seasonalizing x of t, right? So we want to de-seasonalize x of t, so we divide by the season. Now, all of this notation down here, it means that it's our seasonal adjustment factor for whatever month t is, right? So if we just observed October, then we use the October seasonal adjustment factor. But the last time we updated this was a year ago. So we use the one from that we updated a year ago, the last time we observed October. All right, so we de-seasonalize x of t. And then if you think about the trend, if the level of the time series one period ago was at minus 1, and if the slope is b, then we would expect that the new level of the series would go up by 1 times the slope, right? So we update, so our updated level based on the previous forecast would be the previous a of t, at minus 1, plus 1 slope. So updating the new level using our old estimate plus the most recent data point de-seasonalized. Okay, so first, that's step one. We update a of t using this formula. The next step is we update our slope parameter. All right, so we take the current level that we just updated and the previous level from the last time. And the difference between those is our most recent observation on the slope. It says in the last time period, the time series changed by this much, so that's going to be an estimate of the slope based on the most recent data point. And then we have our previous estimate of the slope from last time. So we update our previous estimate of the slope using basically the most recent data point. So we update our BT using this equation. And beta is the smoothing parameter we're using here. And then finally, we update the seasonal adjustment factor, right? So if we take So A of t is the current level, not accounting for seasonality, right? So if we take x of t divided by A of t, that's an estimate of the seasonal adjustment factor based on our most recent observation, x of t. So this is one estimate of the seasonal adjustment factor for this month. And this is our old estimate of the seasonal adjustment factor that we made a year ago, our updated one a year ago. So we take our old estimate, we update it using the new data. We get our new estimate for the seasonal adjustment factor for this month. Okay, so we've updated A, B, and C. And now we can make our forecast, right? So our forecast, we just take the current level plus 1 times the slope, multiplied by the seasonal adjustment factor, right? And so keep in mind, we just, let's say that T is October, right? We just updated the seasonal adjustment factor for October, but we're trying to forecast November. So we want to use the seasonal adjustment factor for November, which was last updated 11 months ago. So that's where this, that's what all this time notation means here. Okay. So that's basically how you get the forecast. And then there's a whole issue about how you get started. So let's say it's a 12, let's say that your time series has a 12-month seasonality to it, or a 12-month period. Take the first 12 data points and fit a regression line to them. In other words, estimate intercept and the slope by regressing on the first 12 data points. All right, so then you can use those slope, the A and B, as your forecast for for your trend line for the first 12 periods. And then by taking the actual divided by the trend line, you can get an estimate of the seasonal adjustment factor for that month. So if I wanted to kind of illustrate this, you go back here. So, right, so you fit a line for your first 12 data points, and then you estimate your C of t. Right, this is the x of t at time period 1, and the difference between that and the trend line, that would be your estimate of the seasonal adjustment factor for this month. So I admit this is kind of complicated, right? I think if you go back, read through these slides carefully, you can figure out how to implement it in Excel. I briefly mentioned Winter's additive model. It works the same, except that it has an additive term for the season rather than multiplicative. And that would be for time series where the amplitude does not increase with the level of the series, rather the amplitude stays the same. All right, I want to kind of skip all of this about forecast error. I just want to say, well, it is possible to construct confidence intervals on your forecasts, right? So what happened is you're sitting at some point in time, and you can forecast out into the future. You don't have to just forecast the next period. You can forecast the next 12 periods or the next 24 periods, however far out you want to go. And you can then devise confidence intervals on those forecasts. What you will typically find is that the further out into the future you're predicting, the greater is the width of the confidence interval. That makes sense, right? Your forecasts for next month are probably more accurate than your forecasts for 6 months from now. All right. The last thing I just wanted to mention, and I just want to give you what the idea here is, that knowing how to implement it is not particularly important, but I just want to show that there's this idea out there. It's called adaptive forecasting. All right, so it's based on the idea that the underlying behavior of the time series can change, right? So for example, we know that if the time series seems to be behaving in a very stable manner, we want to put either like a big value of M on a moving average or a small value of alpha, so that we include lots of past data and get a lot of averaging effect, get a lot of variance reduction effect. Right? Now the problem with doing that is if something changes, it won't adapt quickly. If, on the other hand, our time series is changing very quickly, we don't want our forecast to lag way behind. And so we might want a smaller value of M or a bigger value of alpha. So the basic idea of adaptive forecasting is you monitor the forecast errors. And if the forecast errors seem to be stable and small, we will use a small alpha and get lots of averaging effect. However, if we see the forecast errors increasing, then we might switch to a bigger alpha to try and catch up more quickly to the changes in the time series. So what we're going to do is we're going to use a tracking signal. You can, I guess one way to think of it is you can think of these values here as the forecast errors each period, right? The actual minus the forecast. And basically you can find some control limits. So basically, as long as the tracking signal stays inside of these limits, we're going to leave alpha alone at a fairly small value with lots of averaging. But if we observe the tracking signal leaving these limits, that's telling us that while something's happened in our time series, we should switch to a bigger value of alpha. So you can adaptively change how much smoothing, how much averaging you do in your time series. All right, so kind of in summary, the methods we learned today, they're not model-based, right? Not really anyways. They're based on updating our forecasts or our estimates using the most recent data. And these basically, that's what I had to talk about today. All right. Real quickly, this assignment is not too bad. I have some new data. This is the daily number of positive COVID tests in Pennsylvania. We're going to apply simple exponential smoothing with alpha equal 0.01, implement that in Excel. And then we're going to use solver to find the value of alpha that gives the smallest root mean squared alpha error. We're going to apply double exponential smoothing to the data. We're going to again use solver to find the best value of alpha. Okay, we're going to apply Winter's multiplicative model to that wine sales data I showed you a picture of. And finally, this is kind of more like a problem, a holdover from last week. I want you to fit the COVID data using an order 14 autoregressive model. So you're going to create 14 columns of time shifted values of the time series, run a regression. Any terms that you find in that regression that have insignificant p-values, you get rid of them and rerun the model with the ones that are significant. All right, and that should be interesting too. All right, so not a horrible assignment, only a little bit of solver, mostly Excel work, a little bit of regression. Okay, that's what I got. How many people are still with us? Oh,
I have a question.
Yeah.
With when you're removing the terms that aren't statistically significant, like what alpha level are you saying?
I usually use 0.05. If it's lower than 0.05, it is significant. If it's above 0.05, it's not. That's what one typically uses. If it's close to 0.05, you can kind of make up your own mind. Anything else? Okay.